research because you are in the very study phase of it. You must having lots of questions. Okay, so please, I will please, sir, carry on. Okay. Thank you.
Assalamu alaikum. Again, we will meet again. Again, we will talk, inshallah, about green chemistry. We talked about many topics like catalysis, like physical characterization of catalysis, like in situ characterization, and absorption. Many topics, alhamdulillah, we covered. And today, again, we will talk about green chemistry. Green chemistry is the most important and recent revolution of chemistry and the other fields as well in the last 20 or 25 years, or maybe less than 30 years. Of course, you know that green chemistry has a main, big, and unique and brief message, which is seek prevention, not cure. Means it's better than to avoid the problem, not to try to solve it. Or it's better than avoid to be sick, better than going to the doctor and hospital and take injection and so on. Okay. Let's go through some about green chemistry. Of course, we will not cover everything about green chemistry because it's very wide branch of chemistry and study. But now we will talk about what green chemistry is. Actually, it started in 19th, and of course, this is a background about its history. And green chemistry offers an alternative to the traditional environmental protection agenda. What is the traditional? What is the traditional environmental protection agenda? Simply that after the disease will come, so we will try to cure it or try to solve it. After the problem will happen, so we will try to build other institutes to try to solve these problems and or make companies for filters to cure the exhaust coming from the industry and so on. But now we try to solve the problem from the beginning, or it's a kind of solve the problem from the beginning. Actually, I told you, it needs, there are three driving forces that facilitated the advancement of green chemistry. What are these three driving forces? First is everybody is governed by his government. Means we are following our government in all things. Whatever government says, we are doing it. Okay. First, should be some rules comes from government, which is national legislation, which says which gives us the rules of please do something and don't do this thing. So legislation should come from the government first. Second is people or the community or everybody should have this culture of keeping the environment safe and doing green experiment or doing experiment without using harmful or pollutant or hazardous chemicals and so on. The third is this one is economic benefit. What is the impact of green chemistry on economy? Of course, economy will be impacted in a great way or a great amount, as we will just see in the first slides, in next slides. This is legislation, and it happens. And in economy, we will not focus on this. This is the effect on economy that it decreases capital investment. The government will invest much about curing and decrease operating costs, and also reactor space time yields go up by using less or no solvent. Try to decrease the solvent, replace stoichiometric reagents with catalytic cycles process will run at ambient temperature, less than high energy, or eliminating waste, and also finally replacing toxic reagents with beings benign ones, saves on safety costs during transportation and storage. All of these are the benefits which return back on the economy of our nations. And these are strategies, like scheme, strategies, goal. It should go to practical approaches through operating tools, and monitoring tools will monitor this. Uh, what about the history of this of the green chemistry? It started at 69 by Oman, made a kind of article, published it, and then Nixon, the president of United States, makes a kind of legislation, as we just mentioned, and steps come on, until we reached the 20s until now. Of course, we had some kind of mini registration and many conferences, as will come soon. In 19th, those people, Paul Anastas and John Warner, made 12 principles for green chemistry. It will be like this. All of these are 12 rules of green chemistry. All of these rules have the what we just mentioned, that decreasing the amount of energy, decreasing the stoichiometric reagents to catalytic reagent, and decreasing the pollutants, and so on. These are the 12 principles of those two people, which has been celebrated 25 years of starting green chemistry science, or green chemistry idea, maybe a few years before. And those are the principles of green chemistry. Those are applied in USA and Europe, but African people started to make the same conferences, and started to be jealous, and they made a conference at 2010, a very big conference. It focused on greener Africa. Those are the principles of the green chemistry topics, which was offered in this conference. Now let's go to uh, our interest in green chemistry. Green chemistry for us, we will think about two items. The first one is we have to think about geosynthesis methods, which will help in decreasing the pollutants. And the other thing is organic solvent retirement, means we have to avoid organic synthesis. We have to use green methods that we will just mention about it. And also we use renewable or initial reagents, which is a way of chemicals, and try to make it dream reactions, and clean reactions and green reactions, like it is called sometimes dream reactions, means it's a dream. We can't reach it 100%, but we are trying to go through and try to achieve sometimes. Now, how green is this process? It's a very big question for any process. When you are making a process, you would just ask yourself, is it green or not? Like if you, for example, if you make a reaction, this reaction is, for example, alkane or alkene, sorry, with HBr, for example. It is break for double bond, and the H will be on this carbon, and the Br is in this carbon, and bromo alkane will be obtained. It's very cute, very nice. No hazards, no nothing, no other waste, or no other side products or something. But still, you ask yourself, is it green chemistry or green reaction or not? There are some things out of the scene. You can't see it. You only look at the equation and think it's green. It's very nice. 100% no waste, 100% product, and very good. But still, the question will come to you soon. Where did you bring this HBr? Where will you keep it? And is it hazardous to use it or not? HBr, I am not talking about the product. Let's have some reactions have 100% atom economy, but you still it's still problematic. We will have this kind of example, like using this in this reaction, alkene in plus HBr, it gives this Br, and of course we have a very big question as well for fuel cell. Let's see, is it clean energy or not? Fuel cells are very clean energy because in hydrogen membrane fuel cell, for example, it takes hydrogen from you with some oxygen, all are going to the membrane, and finally gives you energy, a very beautiful energy, very clean energy, and water as side product. It's very nice. Water, clean water as side products. But still, the question will arise. Is it clean energy or not? I'll just give you a simple example. We have just ate bread in this room, and you have just tasted a very nice bread. Where did this bread come? Somebody just cook it. And before this one cook this bread, where this come? There was a flour which was just paste and put in the oven and became a bread. What is the previous step? This flour was grains, that is just grained to be flour. What is the previous step? There was a farmer who planted this and took several months to take care and irrigate and took lot of effort. This is the history of this product. And what about the history of fuel cell? Not only fuel cell, what is the history of hydrogen used in the fuel cell? This is the history of this hydrogen. It should be 100% or 99.99% purity. How can we get this purity of hydrogen? There is no natural source of hydrogen. So we have to prepare. How can we prepare? We have to go to fossils and try to make reactions of these fossils. And what will happen? Let's have this and try to understand how green is this fuel cell. And this will make you to think deeper, not about what you see, but you will think about what's beyond the scene you are looking at. Of course, fuel cell, this is the simplest idea of fuel cell. Hydrogen goes with oxygen to the fuel cell on the catalyst inside fuel cell. Heat or energy will go outside, and water as side product. This is schematic diagram for this process. As you can see, water comes as fuel as side product. Is it clean and or green energy source? Is it? Then you can see here that it is a kind of this process. Adding this high efficiency to the environmental benefits, no emissions will come, CO2 or NOxes or SOxes or hydrocarbon particulates will not come. So it is very clear. But and the problem is where this hydrogen is coming from. This hydrogen is coming from burning or reaction of fuel cells, of fossil fuels, which are like this. Of course, at very high temperature, 700 or 1100 degree, steam water is with CH4. It give us at high temperature. It give us hydrogen, yes, but with hydrogen there was CO. What's CO? CO is a very dangerous pollutant. We have to get rid of CO, right? We have to get rid of CO. This is a problem. Also, of course, this high temperature, it is against the green chemistry main idea or principle, because this high temperature, it's a kind of power or electricity or energy. Where shall I bring this energy? It's a kind another story. And of course, and there is another problem, which is hydrogen is from this process is not pure hydrogen. So it has maybe 2% or 3% of CO. So I have to take this hydrogen and purify again and again until I break until the pollutant or CO doesn't exceed 0.01%. This means it is very low amount of CO. Because what is the problem of CO? CO goes to inside the fuel cell and attacks the active sites, which is on the membrane, like platinum or so, on the membrane, and it is inhibited. It kills the active sites because CO attacks metal, and then it becomes poisoned and kills the catalyst, kills the membrane. So fuel cell will go down, and no energy will be obtained from this fuel cell. This is another problem. So several problems from here, and we have to act with these problems. Another source of this hydrogen is a water gas shift reaction, which CO plus H2O equals gives CO2 is another pollutant, and hydrogen comes to the scene here. But and also we need to purify this reaction. After this explanation, how do you think about fuel cell? Is it clean energy? Actually, it reminds me with those action movies, which the hero goes to save a cat or something, very something, okay? And to his way to save this cat, he kills many people. Oh, those are souls as well. Those are humans. Why did you kill them? Okay, but still, he kills many people to save something. Okay, and here we killed how much persons, how many persons, how much pollutants we released to get pure hydrogen to use in the fuel cell. We have to think about this issue. Of course, there is another problem about fuel cells, because you use hydrogen as a fuel. If you get this hydrogen, pure hydrogen, you have to transport it from its production area to its usage area, to the place you will use it. Okay, this is another problem. This how to save it or how to store it, and how to transport this amount of hydrogen. This is a very long story. Of course, now we can determine is fuel cells is considered as a source of clean energy or not. For its unit, only the unit after obtaining hydrogen is for only this unit, it's okay. But overall picture, we have to reconsider about this issue. Okay. Now, I think we can go to another step for green chemistry, which is quantifying the environmental impact. What is the environmental impact of green chemistry? What is the relation between the environment and the green chemistry? We will check in these we will have few expressions that we will make it clear. First of all, we have to know what's efficiency. Efficiency is about the conversion and selectivity and yield. We will study about it. And also we have to know something called E factor, which is environmental factor. This is the impact of our reaction on the environment. And lastly, we will know about what's atom economy. Atom economy. I think it's clear from its name, but we will explain at its time, inshallah. First of all, the conversion. Of course, everybody knows that the conversion is the transformation from reactants to products, regardless the type of product. Means any type of product will be okay. I mean, conversion means transformation of reactants to products and full stop. Is it desired product or waste or something? I don't care. This expression, me care. But this expression doesn't care. Okay? The conversion. The reactant conversion is the fraction of reactant molecules that have transformed to product molecules. Like this reaction, methane plus water gives hydrogen plus CO. Of course, if methane point is the remaining after time goes, if the remaining is 0.3, the converted is, there is a mistake here. It should be 0.7 is the converted amount, and hydrogen H2O some 0.7 moles has been transferred to products, and the conversion is calculated like this. Conversion equals 0.7 over the initial amount, which is 1 divided by 100 equals 70%. Then the conversion is 70%. Okay? This is conversion. So what about selectivity? We already talked about selectivity in previous previous lectures. And the selectivity, of course, is the amount of the desired product related or over compared to the reactant. This is high selectivity. High selectivity means less waste. Less waste. High selectivity means less waste. If I use high selective reaction, high selective catalyst, this means I am decreasing the waste that I get, and similar and cheaper separation units. This is good. Of course, if we have many waste, this means we will have many separation units and many costs. This is the equation we calculate the selectivity. Percent of selectivity means the desired product over undesired product multiplied by 100, or the products multiplied, or the reacted amount desired by divided by or multiplied by 100. Now go to the yield. This is the third part of the first one, which is efficiency. The yield, of course, the yield, it should be. We have two types of yield. The first one is theoretical yield. If we have H2 plus O2 equals H2O, this is the theoretical yield. Means if I have 1 mole of hydrogen and half mole of oxygen, it will give 1 mole of H2O. This is the theoretical yield. But did this reaction reacted completely or not? At this time, I'll go to real yield. Then the yield can be calculated by this equation, conversion by selectivity, and the theoretical yield we have just talked, and the actual yield, or then the percentage is the actual yield divided by theoretical yield multiplied by 100. All of these three items are talking about how much converted to desired or undesired product. But let's go to the items which are in contact with the energy, the green chemistry or the environment, which like environmental factor. The environmental factor is very important, and the atomic economy as well, as we will discuss very soon, inshallah. Environmental factor. The impact of our reaction on the environment. This was produced or introduced on 1994. It was a very recent expression. This is how can we calculate the environmental factor. It is the waste amount over the products. This means if the waste is high, then the environmental factor is high. Okay? If the waste is high, then the environmental factor is high. If the waste is low, then the environmental factor is low. Okay. This means that if you are producing very fine chemicals, this means you will have a lot of waste or less waste. You will have a lot of waste. I'll explain. Very simple that if you are going to your laboratory and your teacher asked you to prepare this kind of product or chemicals or any compound, and you just prepared it in a crude amount, you didn't clean, you went to your teacher. He simply asked you, oh, it's not clean. Please go and purify it. Then you will go and you solute it again in another solvent and make recrystallization, and you separate new crystals and the solvent and the impurities was there. You will just throw it in your in the pipes. Okay. After that, you may clean these crystals again. You dissolve it and in another solvent, and you recrystalline again and throw the other one. This means that the waste of solvent and impurities you throw increased or decreased? Increased. Okay. So you just polluted the environment more and more to get purity, high purity of this substance. That's what I mean. The waste, once you need more pure or more purified substance, this means you just make more pollution to the environment. That's why E factor, and the E factor is the waste amount over the products. Here we will if this in these reactions. Of course, I want to explain something about these reactions, which is methane plus H2O gives hydrogen plus CO. If you are looking for CO in this reaction, this means H2 is the waste of your from your products. If you are looking for H2 is the H2 is the desired product, then CO is the waste. Okay, whatever you have other than the desired product is a waste, even if it's very pure water, as we just discussed in fuel cell. The relation between E factor and the purity of the compounds. How do you think? Do pure compounds have high or low E factor? That's what we get from this table. If we are going to prepare or get oil, make oil refining, then the E factor will be 0.1. 0.1. However, if we go to pharmaceutical and fine chemicals, the E factor will be very high, because to get this high purity means that you waste lot of waste. Okay, lot of energy, lot of solvent, lot of waste will come out. But if you don't need high purity chemicals, this means you will not need to make purification. You will not lose solvents and make kind of purification. Okay. So E factor increase substantially when going from bulk chemicals to fine chemicals and specialties. The petrochemicals and the bulk chemicals are the least pollutants, and so on. The smaller E factor and the closer atom efficiency to 100% are the greater process or reaction is. I think it's clear, I hope, and I'll go to the other factor, which is the atom economy. Atom economy, simply, you have learned a lot of time before that energy is not invented or is converted to from a form to another and doesn't create it or destroy it. I'm sure you know. The same rule is going to the mass. The mass also is converted to from a form, chemical form, to another chemical form without losing or gaining any amount of mass. This is, of course, you know this. This rule was carried by this man. The mass is neither created nor destroyed in a chemical reaction. In atom economy, you are looking for what did you use from these reactants. If you have carbon and hydrogen and nitrogen and etc., which of these atoms have been converted to desired product? You are looking for desired product from atom economy. You are looking for desired product. So if you go from these atoms, all of these atoms are going to desired product, this means your atom economy is 100%. But if you lose some of these atoms to undesired or waste products, this means your atom economy will be less than 100 and whatever. If your atom economy is much closer than 100, you are very okay. You are in green chemistry level. But if you are away of 100, so you are away from green chemistry. Okay. Uh, of course, we just mentioned no atoms are gained or lost in a chemical reaction, of course. However, some atoms in the reactants may not end up in the desired product, but they form side products. Here, one considers how many and which atoms of the reactants are incorporated into the desired product. Let's go to this reaction. For example, how can we calculate the atom economy? It's very simple. If you calculate how much atoms or how much weight you are going in this reaction as reactants, and how much you gained as a desired reaction, then you will get easily to calculate the atom economy. In methane is 16 and water is 18, so hydrogen comes out is 6, CO is 28. Of course, it's very simple that the incoming or the amount or the mass in the reaction or as reactants are the same, is the same mass as products. So whatever, so we can calculate the atom economy in either one of these equations. Atom economy is the mass of desired useful product over total mass of all reactants or total mass of all products. It is the same. All are the same result. Let's have an example. This is atom economy as an example. Hydrogen can be manufactured by reacting methane with steam like this. CH4 plus H2O gets 3 H2 plus U. Of course, you can calculate the molecular weight of each of these by in this way. It is the same as we mentioned. So total mass of reactants, molecular weight of reactants is 34, and the total of products is 20 is 34 as well. It's the same. Okay. So atom economy will be calculated as if you are looking for hydrogen. So hydrogen is 6 over 34 by 100. It will be 17.6%. This is the atom economy. And I think in this reaction, you will get to know that how much harmful the use of fuel cell if we produce hydrogen in this way. Because atom economy here is 17%, where we are just announcing that fuel cell is pure energy, but it is we get hydrogen from impure method. Atom economy for this this is another example. You can simply calculate it, of course, and get to know that how much is the atom economy. Atom economy in this reaction is 51. So let's ask a question. Let me ask you a question. When can we get atom economy equal 100? When we get single product. When we get single product, this means uh, you have 100, you have atom economy is 100. How can we get single product? It's a lot of reactions can single product like this. C2 plus C2H4 plus hydrogen equals C2H6. This is single product. Or atom economy is gets in isomerization because it's the same molecular weight. And also finally atom economy in this conversion of alcohol, converting between ketos and aldose is also atom economy equals 100 because it's only one product. We get only one product. This means we can calculate atom economy and get to know that, or can we prepare, uh, we can go without side products to atom economy equals 100. And this is another, you can take a picture of this example. You can calculate atom economy of this reaction. If you need, for example, bromide, how will it be, the atom economy, how much it will be. And there is a stoichiometric oxidation of diphenyl methanol to benzophenol. In this, you will calculate atom economy of this reaction as well. Diphenyl methanol with in the aid of in presence of chromium oxide with sulfuric acid, it will get benzophenol plus chromium sulfate and H2O. Of course, we can calculate the E factor and the atom economy. And for this example, as we just mentioned now, we can calculate the atom economy. And I think we can say thank you very much for your attention. And we can calculate this one together, inshallah, after the lecture. Thank you very much. Yes.
Thank you, Professor Zen, for a wonderful and the most understandable lecture on point of view of the student. Okay, I would like to have some remarks because he had started his lecture from the fuel cell membranes. So I would like to share one of my personal experience which I had encountered during my PhD days, probably in early 2000 or 2001 or 2002. I would pursuing the same experiment of the sulfonation of membranes on polypropylene and polyethylene, right? As he said that in case of the fuel cell membrane, the water is your reactant and water is your product. Okay, from one side you pass on the water and there is a barrier or it is a catalyst. It is acting as a catalyst which basically split your water into HIN and OHIN, right? So from that bond you get the energy and that energy is used for the particular purposes which you are going to utilize. Basically, we were using the polypropylene and the polyethylene membranes. These are the most toughened, or you could say, the most stable polymers, right? What we had to do the sulfonation of these membranes to add on HIN or a kind of, transportation which is basically needed for the transport of H and OH ion. Okay. The experiment was to have the sulfonation SO3H. We had to add on the SO3H onto the polypropylene and polyethylene. The purpose, for this purpose, the chemical which we were using, that was chlorosulfonic acid. Chlorosulfonic acid, one of the strongest oxidizing agent or one of the very strong, I would say, acid. And as soon as I dipped my membrane, it was having a size of 1 by 1 or 2 by 2, I don't remember exactly. As soon as I dipped my membrane into the solution of chlorosulfonic acid, irrespective of molarity, it was sometime 0.001. I reduced the molarity to even to 0.001 molar. But as soon as I dipped my membrane into that solution, it burned. It charred completely. I repeated the same experiment multiple times, but I was not able to do. The moral of the story is that if you think that whatever experiment you are doing today, you are not able to perform, it doesn't matter. It doesn't any way lead that you won't be able it to perform in later years. The same experiment with polyether ketone film, we better call them as the peak membranes. When I joined as a faculty in Jamia, then there was one of my scholar who joined with me in 2009. Her name was Dipti Gautam. Right now she is in England. So we started working onto the fuel cell membrane, and the same experiment I stated to her that Dipti, I was not able to do this particular experiment while I was pursuing my PhD. And those polyether ketone films we got from Solvay. You know Solvay? Solvay is the second largest company all over the world after DuPont. So we wrote to Solvay and we said that on polyethylene and polypropylene, I was not able to perform the same experiment. So we right now we wanted to move on to the toughened polymer, which is polyether ketone. Those people, they sent us 12 A4 size film to me, and Deepti has completed her PhD on that. But the similar problem, the similar incident reoccurred as soon as she dipped her membrane into the chlorosulfonic acid solution. It jarred again, it burned, and she came after repeating the experiment several times. She said, "Ma'am, this experiment cannot be performed, and we are supplied with a limited number or limited amount of the polyether ketone films." Okay, so I was sitting on my table. I said, sometime what happens, you just need to use your wit, your, I would say, your common sense. And that time I was very small. When I was pursuing my PhD, I was not, loaded with this much common sense, or you would say the experience. Sometimes we answer our question with the experience, not with the knowledge. So I was sitting just like that on my table. Deepti said me, "Ma'am, as soon as I dip my film into the chlorosulfonic acid solution, irrespective of the molarity, how low concentration I am going to make it, even then the membrane is going to get charred." So I said, "What is happening? What is happening, Deepti?" Um, I think there is a highly exothermic reaction. Okay, so how uh, how can we control the heat which is liberating? If there would be a way, if we are able to control that heat, probably the experiment would go into the forward direction. And that time I was having very limited amount of infrastructure. I joined in 2006. The same experiment I was repeating in 2009. So I said, "Okay, what we do? Let us control the temperature." So she asked me, "How?" I said, "Put everything into the freezer." We had a fridge, then automatically all the solvent and your membrane, they would be attaining 0 degree. Okay. So as soon as you see on the thermometer that 0 degree centigrade has been, attained, what you do, just dip your membrane into the solution and put it again into the freezer. She did. You won't believe, we performed the experiment. So, unfortunately, we were not able to, do the fuel cell experiment because I was very young and we were not able to get the proper collaborator over there. But that was the finest experiment which we have ever performed. And this basically happened because of those catalysts, or you would say the kind of the experiments we were performing with the common sense. So why I stated this particular incident, because don't ever think that what you are not going to perform today, with the discussion, with attending such kind of the program, if you are not able, probably you would be able to tell the people what was your experience, and from those experiences your student would be able to do the similar thing. Okay. So thank you so much, Professor Zen. It was a very nice lecture, and I myself learned so many things and so many minor things which we actually look over or we don't consider important, but they are very very important to perform our experiment, as well as while we analyze the data, while we compile the same thing into the form of a publication. Thank you so much, and thank you so much for your patience. Let's join for the lunch, and we'll see you after lunch. Okay.